Good morning to all. It is my great privilege to have this national workshop on calibration and measurement uncertainties for balances and the weights. Actually, I think that the calibration and the measurement uncertainty of mass and the balances plays a very important role in everybody's lives, because whether we are doing the calibration of volume or calibration of force torque, everywhere mass plays a very important role. Today we have with us our Honorable Joint Secretary Sir, Shri Vinit Mathur Sahab, who is here with us to encourage us to inaugurate our workshop for today. He is basically an Indian Postal Service officer who is a very senior officer in the Joint Secretary in the Ministry. And being an engineer from IIT, he understands the technicality of the subject, what is the legal metrology, what is the calibration, and what is the measurement uncertainty. I am actually fortunate enough to work under him since last more than 2.5 years. I am working under him, so I have learned a lot from him. Sir, I would like to request kindly say few words to our panelists, to our participants, and motivate all of them to understand the very dry subject, which is balance and the weight. Sir, please.
Good morning to all the participants and the esteemed guests on the panel. I think Dr. Julian Haller, the scientist from Sartorius, Germany, is going to give you a very detailed brief on what exactly is the uncertainty in non-automatic weighing balances, and what kind of maybe a tolerance level we can have in these kind of machines. Now, it is heartening to see that this is another great workshop which our team from RRSL Ahmedabad, under the guidance of Deputy Director Shri Ashutosh Agarwal, is organizing, and under the leadership of our Director Shri Badrinath Dikshit, who is the director in the ministry. We have been holding these workshop sessions for the participants, industry, the stakeholders, scientists, and the policy makers per se, so as to understand what are the nuances which are majorly appearing in the industrial issues and the problems which they report, which possibly we should be able to support them and correct them. Now, this is an important subject where the workshop is being held, because a large part of our 5 trillion economy, which we are envisaging in the next few years, is dependent on the weights and measures. And legal metrology being one of the finer arts of measurements, needs to be corrected in the society and in the commerce and industry and trade, so that everyone has great faith in whatever are our weighing machines, whether they are automatic or they are non-automatic machines, but their calibrations and maybe the fine-tuning to the requirements of finer measurements to microseconds or to microweights and grams and nanograms is correct. And therefore, it is of great importance that our manufacturers and our users understand that how this calibration science works and what is in the benefit of every one of us here. Now, we from the government of India have been trying very hard and very well that we organize our weights and measures machinery down the line in the state governments and align our departments so that they are able to understand as to how this particular calibration and other things can be made more easy. One of the requirements of the government is ease of doing business, ease of supporting, ease of licensing, and many of the other things. And we from the central government in the government of India have taken a lot of measures to bring in transparency into our association with either the industry or the manufacturers and all the stakeholders. And this has worked wonders. There have been a great movement in the legal metrology science, and it is transmitting into great output for the industry per se. I hope this particular session, where the finer nuances of how the calibration and the measurements in non-automatic machines need to be correct, and what measures can be taken by everyone, whether he's a merchant who's using the machine, or a manufacturer, or maybe an inspector or a policy maker at the national level. What better we can do in this particular area is our thrust. And I understand that a lot of suggestions and possibly corrections can also be available in this particular workshop. And by the end of the session, we'll be in a better position to support the industry and the trade across the country. Internationally also, whatever we are manufacturing, we are selling, whether the mates and the machines which are being exported are internationally used, becomes of great importance. So I think Ashutosh will steer this session, and we'll have very good suggestions at the end of this session, which will bring more insights and enlightenment for the government of India to move forward. With these few words, I thank all the participants for coming on a Saturday morning, and maybe for RRSL for organizing such a brilliant workshop. Thank you very much.
Thank you very much, sir, for your always motivating and lightning words. Certainly, sir, you are always, you are just a light of hope for the legal metrology behind us. We are looking towards you for all type of help, how we can do better for the society in the field of legal metrology. Certainly, sir, this legal metrology plays very important role in everybody's life. Whether, sir, yesterday, just before some days, I just tell you, sir, one example. We have issued an advisory under the leadership of our honorable director, sir, that all these edible oils, what they were doing, they were declaring volume with the temperature. And due to this problem, now the volume was 1 liter, but the weight was continuously reducing. So we have issued a direction that you have to remove this temperature, you have to declare volume and the weight, but the temperature should not be there. And at every point of time, this volume should be 1 liter. So these are the things how we are trying to support to the industry in the country and the consumer in both ways, so that the industry which was actually giving the correct quantity, they were being cheated, they were regularly crying. So this type of problems are not only creating the problem for the consumers, but also for the industry. So, sir, with these words, I would like to thank you, sir. You on these Saturdays, I know that you must be working at home, whether in the office or the home. Saturday and Sundays for the officers is nowadays is not like holiday. You must be working over there, and and you have taken your time. Saturday, sir. Thank you very much, sir. Thank you. Now I would like to request our director, sir, Shri B.N. Dixit, sir, who is here to support us. He is our beloved director, and I know that everybody knows Shri Dixit Saab since the beginning, who is regularly trying to help the industry, trying to help the legal metrology fraternity by developing the equipments, by developing the laboratories. Large number of laboratories are being made, established under his leadership during last 10, 11 years, and large number of equipments were given to the state governments. New technical facilities, testing facilities have been developed in the states as well as in the RSL at the central level. Sir, kindly speak to us and motivate all the participants for this type of workshops. Please, sir. Dixit, sir.
Thank you, Ashutosh ji. First, I will say the kind words to our Joint Secretary, Mr. Vineet Mathur, that he has given a lot of motivations, and he is always encouraging us to continue the seminars, and he is giving his inputs also uh, to encourage the participant and everybody. The current seminar organized by you is very fruitful for the laboratory as well as the uh, mm, uh, traders also, where the high technicals trading is going on today. Because the matter of the precision, weight and balances. So when you talk for weight, so what is the correct weight that you have to define? And unless you are not having the correct weight, you cannot calibrate the balance, and the whatever reading will be there, that will be not correct. So the relation between weight and balance is very close, because the balances readings is always depending on the mass by which it has been calibrated. Therefore, the mass that should be calibrated from the higher standards according to the class of the accuracy of the balances. If it is not at least one third of the least count or error of the balances, certainly the problems will in the reading of balances will come. So Ashutosh and his team is having very good presentation from Mr. Julian in respect of measurement of uncertainty and other type of things. So I hope that this seminar will be very fruitful for everybody. You know the value of the RSL, you know the value of National Physical Laboratory, how they are interlinked. The RSLs are interlinked between state and NPL. That's reason the consumers are getting the correct quantities. If the weights and measures are not being calibrated time to time, so consumer will never get the correct quantity. So it's the work of RSL seems very small, but it is not small, but it is of very importance. And if these measures will be stopped, then consumers will be cheated too much, and consumer will not get the correct value, and the reading of the balances will be different. You know all the things. That's the reason the maintenance of the traceability of the weights and measures is very important. And the importance of weight and balances will continue only then when the weight is calibrated with a higher level standards and the balances is calibrated with the respective mass values. So thank you with these very words. I hope that Mr. Ashutosh Agarwal and his team will enlighten the programs, and I will also achieve something there.
Thank you very much, sir. Thank you. Thank you for a kind word, sir. Actually, sir, we have today with us Dr. Julian, who is basically the scientist from PTP Germany. Now he is working with the Sartorius, and we are actually fortunate enough to have him here with us, with our participants, so that we can understand how the calibration can be done, how we can find the measurement uncertainty. Measurement uncertainty is very important factor which plays in everybody's life, not only in the calibration or something testing, but in the everybody's life. Uncertainty is very important part which plays a very important role. So, sir, first of all, now I would like to request Professor Dr. Julian to kindly start his presentation. Sir, Dr. Julian, we are fortunate enough you are here, and I know that you are having a lot of experience in Sartorius, in PTP Germany. You have done a lot of work. Even I know that you were in the meeting when we were discussing in OIML about the digital transformation group, and in the digital transformation group you were there on behalf of Mr. Our old friend from Sartorius. So I think next time I would like to take your presentation on digital transformation also, how we are working on this digital transformation at international level. We will take your help, and certainly we would like to take your help for developing this digital transformation in our country, in India, if you can help us in any way. Thank you, sir. Please, Dr. Julian, sir, please.
Good morning, ladies and gentlemen, and dear Mr. Mathur, dear Mr. Dixit, dear Mr. Agarwal, thanks a lot. Actually, it's a pleasure for me to have the possibility to give this presentation today. Actually, sorry for being late. I always had problems with WebEx for any reason, but now it works. And now let me share my screen, and then hopefully you see my presentation.
Yes, we can. Yes, we can.
Perfect. Okay. So, yeah, as mentioned in the introduction, my name is Julian Haller. I'm working for the metrology department of Sartorius since, I think, 6 years. And before that, I worked for the PTB, the National Metrology of Germany. The topic of my presentation is measurement uncertainty of weighing. And you hopefully know measurement uncertainty actually is a very generic topic of metrology. And actually, measurement uncertainty of weighing is one of my favorite topics, as you will hopefully notice during the presentation. So let me just start with the overview or agenda. I will start with a very brief introduction about measurement uncertainty in general. Measurement uncertainty is a very large topic, and you can probably talk about that for days. So I will really have a brief introduction. Then explain something about the uncertainty of a calibration of a weighing instrument according to the calibration guide Euramet CG18. Then about the uncertainty of a weighing result according to Euramet CG18. And then finally, about the minimum net weight determination based on this uncertainty calculations, also according to Euramet CG18. To start, measurement uncertainty, just as mentioned, a very brief general overview. There's mainly two really important documents that are like the Bibles for measurement uncertainty. The one is the JCGM 100, which is also called the GUM. The title of this document is Evaluation of Measurement Data Guide to the Expression of Uncertainty in Measurement. It's published actually, as you see, by the BIPM, and which is quite nice, it is freely available, can be downloaded from the BIPM website. This is a very comprehensive and long document, and if you read that and understand all of that, you will probably know everything about measurement uncertainty. But admittedly, it's a quite complicated document. So the BIPM also published another document, the GCGM 104, as an introduction to the GUM. That is much shorter, much easier to read. It's also freely available, and I would really recommend, if you want to learn more about measurement uncertainty, to look for this document and maybe read it. And if you then want to learn more about measurement uncertainty, read the GUM, the JCGM 100. So as mentioned, they are both freely available, can be downloaded from the BIPM website, very helpful documents. Also from one of the documents, actually from the GUM, I would like to start with a definition of uncertainty of measurement uncertainty. And as it is written here, the definition is that the uncertainty is a parameter associated with the result of the measurement that characterizes the dispersion of the values that could reasonably be attributed to the measurement. So that is not easy to read and to understand, but that's the official definition. And if you read over it 2 or 3 times, then you probably get the definition. It's also quite important to mention what is given to this definition in the GUM as note number 3. It should be understood that the result of any measurement is the best estimate of the value, and that all components of uncertainty contribute to the above mentioned dispersion. And we will see what all components of uncertainty means later on. What is usually stated by convention is the so-called combined expanded uncertainty. And that is actually, practically, it's an interval within which the true value lies within a probability of approximately 95%. And it is usually stated as that. So you have any measurement result, for example, 100 gram, with an uncertainty of 1 gram, and then it can be stated like this. And this actually just means with 95% probability, the true value is within the range 100 minus 1 gram, 99 gram, to 100 plus 1 gram, 101 gram. And in diagrams or graphic representation, it is usually denoted by respective uncertainty bars. Just for very strict or correct terminology, they are often called error bars, but they are not, they are uncertainty bars. And if you see something like that with a respective uncertainty bar, you will see this just means the uncertainty, the expanded uncertainty, the maximum and the minimum of the above mentioned interval. And if you would have a look at the respective probability distribution, it would usually actually look like this. So if you have the measurement result, 100 gram, and then the uncertainty ranging from 99 to 100 gram, of course, you have the highest probability that the true value is really where you've measured, and the probability decreases the far further you go away from that indicated or stated measurement result. Now, why are measurement uncertainties important? So, of course, at first, it will always give you general information about the quality or reliability of a measurement result. So if you just compare these two examples here, in the left example, you have quite high reliability that your measurement result of 100 gram is approximately correct. But if you have a much higher uncertainty, now this is a really extreme example where the uncertainty is even bigger than the measurement, you would see that this 100 gram actually is really not reliable. Actually, the true value would, in this example, be between minus 100 gram, whatever that means, let's say 0 grams and 300 grams. Yeah, so it gives you an information about the reliability of your measurement result. It also allows you to do reliable comparisons of measurement results. And let me just explain that with one example. Imagine you are the boss of a company or of a laboratory or whatever, and you want to find out if your two persons, your staff members, or your two lab sites, if you have different lab sites, if they measure the same. Now, what you would do is, of course, you would let them measure the same thing, whatever it is, doesn't matter here. And they get this result for person or lab E and this result for person or lab B. And you do that again, and then a person or lab A will yield this result and person or lab B this result. And now you as the boss or as the lab manager or whatever have to decide, are they measuring or are they getting comparable results? Are they compliant with each other? And this is of course hard to say now. You would probably say, okay, here the difference is big. Here the difference between the two results is not that big, but you can hardly reliable make any statement. And this of course looks much different if you take into account the measurement uncertainties. Now, in the left example, you will see there is an interval or a region where the two results, including the measurement uncertainties, overlap, which means if the true value is here, actually both persons or labs have respectively measured the correct result, which means these two measurements are compliant with each other. But in the other example, you see there's no overlap, which means they contradict each other. So in this example, you as the boss or lab manager would have to, of course, undertake respective action to either find out why person or lab A or B measures not correctly, or if they have to state bigger uncertainties. Actually, it is really not possible without considering the measurement uncertainties to say whether different results are consistent with each other's. And the third reason that makes measurement uncertainties so important are reliable conformity statements. So like pass, fail, or intolerance, out of tolerance. And again, let me explain that. Just imagine you have 5 measuring instrument, maybe weighing instrument, doesn't matter. And they measure something, or you have determined a respective measurement from them, and whatever it is. And then you have a respective tolerance. And now what you would say now, of course, is that weighing instrument A, B, and E are in tolerance, and C and D are out of tolerance. But this looks different if you take into account the measurement uncertainties. Now you would honestly have to say, well, instrument A is intolerance, that's a pass. Instrument D is out of tolerance, so it fails. But for the other ones, you just have to say, well, B and E, they are probably in tolerance, but it could be that they are also out of tolerance. So this is something like a probably pass. And for instrument C, you see it would also be possible that in the true value is in tolerance. So for this instrument, you would have to state it is probably out of tolerance. So again, it is not possible without considering measurement uncertainties to make reliable conformity statements. Measurement uncertainty has to be taken into account. Now, something that is clear to, let's say, metrologists or people dealing with measurement uncertainty, but sometimes is a bit hard to explain to users or also, for example, to our marketing department, is that every measurement has a measurement uncertainty. It doesn't matter if you pay 1 million euro, 2 million euro for a measuring instrument, it still has a measurement uncertainty. It may be smaller, but it still has one. So it is really important to keep the measurement uncertainty as small as possible. And that is, of course, the task on the one hand of the manufacturer of a measuring instrument to manufacture a high quality measuring instrument. But it's also the task of the user to make sure that his process and how he uses the instrument does not increase the measurement uncertainty. So for a weighing instrument, for example, to consider all these, let's say, typical devices to not to make sure that the balance is leveled, that it is adjusted, that you do not use magnetic probes, whatever. Yeah, so it's the task of the measuring instrument, but also of the user. It is further important then to determine and state the measurement uncertainty as accurately as possible. And this generally is also, and this is a surprise to many of our users, actually it's the task of the user of the measuring instrument. What we can provide, and actually we do that via our service department, is to provide respective help for the user, but generally and formally, it's the task of the user to determine and state the measurement uncertainty of his instrument. And of course, actually, usually in the beginning, it is important to choose test equipment so that its measurement uncertainty matches the task. And this is, of course, again, the responsibility of the user. So very brief or simple example, of course, if you want to measure something in the microgram range, you should not buy a weighing instrument with a scale interval of a milligram. That is, I think, clear to everybody. But nevertheless, it is the user's task to make considerations before buying test equipment that the measurement uncertainty matches the respective task and the required accuracies. Now, measurement uncertainty determination, as mentioned, usually follows the previously mentioned GUM as a document, but there's not the one correct determination of a measurement uncertainty because it is usually based on assumptions and approximations. So if you let two different experts or persons do a measurement uncertainty determination for your instrument, you might get two different results. So there's not the one single truth actually. And what you've probably seen in, for example, data sheets from manufacturers, or if you're familiar with that in chapter 41 of the USP for small loads, is that as a rough approximation of the measurement uncertainty, one just takes 2 times the standard deviation of a repeatability measurement. So this is a pragmatic approximation, but it is of course not the whole truth. So that you're just aware, often something like this is stated, but this is just a rough approximation. If you want to have a better approximation, I personally recommend this Euramet calibration guide number 18. That gives a really detailed and sophisticated description of how to determine the measurement uncertainty of a weighing instrument. The publisher Euramet is the Association of European Metrology Institutes, but we do know, as also a globally operating company, the guideline CG18 is not only recognized in Europe, it is also used in Asia, the Americas, so it is quite a global, don't let me call it standard, but global guideline. And the current version that was published end of 2015, it's the version 4, was actually written with several NMIs. So I think the Spanish NMI was involved, and there are several more, and also manufacturers. So my former colleague was also involved in writing this guideline. So it's really, it incorporates the, let's say, academic metrologic view and also the industrial metrological view. And it has a really strong focus on measurement uncertainty. So I'm just showing you the table of contents here on the right side, and I just highlighted in blue the parts that deal with measurement uncertainty. And you see it's about 50% of the complete document are dealing with measurement uncertainty, how to determine it, how to derive formulas and whatever. So really strong focus within this document. And actually, it's a long document, and I would just like to give you a short overview of how the uncertainty of a calibration of a weighing instrument is determined according to this document. Now, sorry, let's start with the definition of a calibration. So the calibration is the determination of the deviation between the measured value and the true value. So what does that mean for a weighing instrument? Well, actually, you put on a weight. And as Mr. Dixit said in the introduction, of course, the weight is so important for the calibration of a weighing instrument. So you do know, of course, this reference weight, because usually you have to use a calibrated weight. So you know, for example, this 100-gram weight has a conventional weighing value, or let's say true value, of 100.00007 grams, for example. And now you read the indication from the balance, for example, in this example, 99.999 gram. And then you simply calculate, and this is the official result of a calibration, the error of indication, which is just the difference between these two values. So in this example, it would be this one minus this one is minus 0.00107 grams. So that is a calibration. And now we want to determine the uncertainty of this value. And as you see, this is what would look like in our calibration certificates that we issue all over the world. You have the test load, which is the reference mass. You have the indication, and then you have the error of indication, just as the difference between these two values. And of course, we state a respective uncertainty. Now, even if you are not familiar with the GUM and how to calculate and determine measurement uncertainties, it is quite straightforward that if you just consider that the error of indication is calculated from the indication and the reference weight, that the uncertainty of the error of indication is then logically actually calculated from the uncertainty of the indication and the uncertainty of the reference weight. Why that is squared here, for example, that is given in the GUM. So if you are interested in the detailed formulas, please, as mentioned, have a look at the GUM. But the general characteristics of this formula, that you have to consider the uncertainty of the indication and the uncertainty of the reference weight, that is straightforward. Now let's have a look at these two contributions. First one, the uncertainty of the indication. And of course, you might say, why and to what extent is the indication uncertain? So you read the indication 99.99 grams. What is the uncertainty connected to that? And actually, you have one or actually two contributions that are always there if you have digital measuring instruments. If your balance shows 0 in the beginning, you just know that the true internal value is between minus half a digit and plus half a digit. And so you do not know what the internal true indication is because you're limited to the respective digitalization of the instrument. And that is actually an uncertainty contribution that we have to consider. The same applies, of course, then if you read the final value, if you read 100 gram, you just know the indication or the indicated value is between 100 minus half a digit to 100 plus half a digit. And that is, of course, then also taken into account. The next thing is actually repeatability or random variations. If you do the same thing on a balance 4, 5, or 10 times, and actually you really try to do exactly the same way, you nevertheless might get slightly different indications for your 5 or 10 repetitions. The reason for that are random variations, maybe due to internal reasons, but also maybe due to environmental conditions. But whatever, this also would mean, of course, that if you do it 10 times, you might get 10 different results, or maybe not 10 different results, but slight variations. So you have to take into account, if you do the calibration only one time, the repeatability as a possible uncertainty contribution. And that actually is the real reason why repeatability has to be measured in the calibration of a weighing instrument. It is needed for the determination of the uncertainty. Next thing to be considered is eccentricity or eccentric loading. Of course, if you calibrate a balance, you should, of course, and I think everybody will do that intuitively, but you should place the load in the middle. But for some loads, it is actually just not possible to put the weights in the middle of the weighing pan. So for example, if you have some test load like, let's say 130 grams, 120, 10 grams, it is just physically not possible to put them into the middle of the weighing pan. And that's why you have to consider eccentricity of the weighing instrument as a measurement, as an uncertainty contribution. And again, this is why in a calibration of a weighing instrument, you have to measure the eccentricity to find out what, for this particular weighing instrument, how large this effect will be. And I just show some, let's say, schematic drawings or paintings here, but of course, you have to calculate actually all the respective effects, and this is the respective formula. So if you are, let's say, afraid of formulas, don't worry. But if you are interested, again, take a look at the CG18. It will give you details about how each of these contributions then is calculated in detail. Everything is described there quite well. Now, the next contribution, as mentioned, is the uncertainty of the reference weight. And again, you might say, well, I have a calibration certificate for my weight. So what is the uncertainty? Now, let's start, of course, with the obvious thing. If you calibrate a weight, you will also have a measurement uncertainty. And that is what you see, for example, on the calibration certificates that we issue. For example, you have that 100 gram weight here. The conventional weighing value is 100 gram minus 0.07 milligrams. But the measurement uncertainty of this value is 0.05 milligrams. And of course, then you have to take that into account when calibrating the balance. What we do actually is for weights below or equal to 5 kilograms, we really take the conventional weighing value and the measurement uncertainty given in the calibration certificate. But for higher weights, for which you only have weighing instruments with a coarser scale interval, it is usually sufficient to consider the nominal value and the MPE of the weight. So that makes it easier, but is only usually sufficient for, let's say, 10 kilogram and above. The next thing is quite complicated. You have to take into account as an uncertainty contribution a possible buoyancy correction. This is due to the fact that if you adjust the balance directly before the calibration, then of course you can assume that the air density at the calibration is the same as the air density at the adjustment, because you do it directly afterwards. But if you do not adjust directly before the calibration, you have to take into account that the air density might have changed between adjustment and calibration. Sorry. So these are two different formulas. I think I will not go into detail because again, a description why the formulas look like this is given in the CG18 and also respective explanation. So this is how you have to take that into account. The next part or the next contribution to the uncertainty of the reference weight is that you may have had this weight calibrated, I don't know, 6, 12, whatever month ago. And of course, if you use a weight, it will change the true value. So you have to take that into account. And this is, of course, usually based on the experience. So if you know, usually my weight between two calibrations of the weight drifts or changes this amount, then you have to take that into account for the uncertainty of your weight. And this is, of course, experience of the owner of the weight for us as a calibration lab or as a calibration lab for weighing instruments, based on the experience that we have with the analysis of changes of our weights. And you have to take account if the weights that you use are not perfectly acclimatized. So if you might have a temperature difference between the weights and the surrounding, you might get convection. So if the weight is colder than the surrounding, then air will actually, that approaches the weight, will cool down, actually then go downwards and cause by friction a force on the weight. So a colder weight will appear heavier, while a warmer weight will appear lighter. And you have to take that into account. And this can only be done by doing a reliable estimation of the temperature of the weights and of the environment. And if you have that temperature difference, again, a formula is given in the CG18 how you can calculate the respective uncertainty contribution. And again, these are just images, but of course you have to calculate that with the respective formulas. And again, these are just the contributions mentioned, but the detailed formulas are given in the CG18. Now, this is how the uncertainty of the error of indication is calculated. So this is the brief formula, and if you then expand that respectively, this is what it looks like. And this is how we state it in the respective calibration certificates. One thing you also see here is the expansion factor. And just to explain that very briefly, for calculation of uncertainties, one usually uses the so-called standard uncertainty. And if you remember, maybe, hopefully, actually from your mathematics class in school, if you consider a normal distribution or a Gaussian distribution of uncertainties, then you might remember these Gaussian or normal distributions cover 68% probability if you go from the mean minus 1 standard deviation to plus 1 standard deviation. And a standard deviation is like a standard uncertainty. So that actually means if you state standard uncertainties, you will just have 68% probability that the true value is within this interval. And of course, 68% is not sufficient. So what is done by convention actually is that so-called expanded uncertainties that are then given with a capital U are stated so that it covers 95.45%. And to do that, you have to calculate the expansion factor. And I'm not going into detail because that's again a quite complicated formula. The Welsh Satterthwaite formula, again, also given in the CG18, also in the GUM, if you want to have a detailed look on that. But just to explain that, K does not always equal 2, which is a misconception that is done or given in many cases where K equals 2 is assumed always. But you really have to calculate that based on the measurement results. And it depends, at least for the calibration of weighing instruments, mainly on the result of the repeatability measurement. Should then be in the range between 2 and 3, as you see it here. And if you have a sufficient reliable repeatability measurement, which is the case if you do 10 repetitions, or if you determine a standard deviation of 0, then K equals 2. And finally, we do also state the relative expanded uncertainty. That's not necessary, but sometimes requested, which is actually just dividing the expanded uncertainty by the respective test load. So you have something in percent of the test load. Now I've presented all these respective contributions to the measurement uncertainty or to the uncertainty of a calibration result. And usually then, if I explain that or train that to our technicians, they will ask, is that really important or does that really play a sufficient or significant role? And then my answer always is that depends. If you take a look at different examples, and that is what I've given here, you will see that the different contributions play a different role for the different examples. So you see that in these red or brown colors, I do note the contributions of the uncertainty of the indication, rounding at 0, rounding at load, the standard deviation, eccentricity. And the blue colors denote the uncertainties of the reference weight. So the calibration uncertainty, the buoyancy contribution, the drift since the last calibration, and convection effects. And then for several examples, I just noted that for the measurement uncertainty or the uncertainty of the calibration, how much each of these contributions contributes to the overall uncertainty. Now let's start with a, let's say, very common example, a typical laboratory balance with a maximum of 220 grams and a scale interval of 0.1 milligram. We use E2 class weights for the calibration, and we say that the temperature difference or the temperature variation at this installation site is 5 Kelvin. And now if you just consider the perfect calibration or the perfect calibration result, standard deviation is 0, eccentricity is 0, and the balance was adjusted directly before the calibration. You see you have different of these contributions contributing to the uncertainty. For higher test loads, it gets the reference weights uncertainty contribution get more important. But if you assume more realistic calibration results, so you have a standard deviation of half a digit approximately and eccentricity deviation of 2 digits, you see that already these respective contributions, the red or brown ones, get more important. But if you use not acclimatized weights, so you have a temperature difference between the weights of between the weights and the environment of 10 Kelvin, you see that these contributions absolutely dominate the complete uncertainty. So it really depends on the particular situation, particular case, and also on the particular weighing instrument that you're calibrating. So if you have a look at a, let's say, higher capacity weighing instrument with a maximum of 72 kilograms and a scale interval 1 gram. We would then use F1 weights, that is sufficient. And if you again look at these 3 different examples, you see that the weight, the blue parts, play a much less important role for the calibration uncertainty of this instrument, but rather the complete uncertainty is dominated by especially the rounding. It's a rather coarse instrument, and also, of course, on the standard deviation eccentricity, if you measure that respectively. So the weights are not that important, even although we just use F1 weight in this example. And actually, just the opposite example, if you consider an ultra micro balance, so a maximum of 2.1 grams and a scale interval of 0.1 micrograms, it more or less doesn't matter what you do. So you see, I assumed really big standard deviation and eccentricity deviations here. But whatever you do, you see that the uncertainty is dominated by the uncertainty of the reference weight. Which just means, if I state that positively, this balance is too good for the weights. Or if I state it negatively, actually the weights are not good enough for that balance. Because whatever you do, the calibration uncertainty actually is the uncertainty of the reference weights. And again, here we are at what Mr. Dixit mentioned at the introduction, the weights that you use for calibration of a balance and their uncertainty and their conventional weighing value is, of course, really dominant and really important, especially for high resolution balances. Now, up to here, I just talked about the measurement uncertainty of the calibration result. And the bad news is that, strictly speaking, this applies, of course, only to the time and conditions of the calibration and is also only given at some discrete points. You usually will have a calibration at 5 or 10 test loads. But so you only have the information about the calibration uncertainty at these 5 or 10 test points. So for the user, this is rather useless information. That might be a bit hard, but actually the user may not use this calibration uncertainty as the calibration of his weighing process. And therefore, actually, the Euramet CG18, fortunately, gives additional information about how the uncertainty of a weighing result in use can be determined. And that is actually the topic of the next part, the uncertainty of a weighing result for the user, according to this calibration guide. Now, let me start with demonstrating how we, and of course also other calibration labs, give that information. So this is again part of a calibration certificate, how we issue that all over the world. We give as further reference notes, additionally to the calibration result, information about the uncertainty of measurement in use or uncertainty of any weighing result. And this is usually, according to the calibration guidelines, stated in the shape of a straight line equation. And we provide a table with sample values. And now let me just give you a brief overview of how this straight line equation is derived. The uncertainty of a weighing result of a user comprises several contributions. So of course you start with the uncertainty of a reading, and that is actually what we've seen before. If you as a user read the indication from a weighing instrument, you also have the contribution for rounding at 0, rounding at load, the standard deviation of repeatability, and possible eccentricity effects. The next part is that now, as the weighing instrument is calibrated, of course, you know it might have an error of indication, and this, as well as the uncertainty of the error of indication, have to be taken into account for the uncertainty of a weighing result. And now the next one is from the calibration on, of course, possibly the device might change. and especially, of course, due to possible temperature changes. We know that there is usually a remaining temperature sensitivity of the device and also buoyancy. So the air density will change with temperature, and this has to be taken into account. And of course, the user might use the weighing instrument slightly different than it was used or done during the calibration. So for example, the user usually might use the tear function, and he might place weights or weighing goods more eccentrically on the weighing instrument. All of that has to be taken into account when stating the uncertainty of any weighing result. So we know already this one, the uncertainty of any reading, mentioned that, uncertainty of, rounding at zero, rounding at load, standard deviation of repeatability, and eccentricity. So that is what we've seen before. And the good thing is about all uncertainty contributions that we will consider in the following, that they can be assumed to be either constant, so it's a constant value over the complete weighing range, or it's roughly proportional to the reading or to the load. Next contribution, as mentioned, is more or less the calibration result. So what we have to do, of course, now, if we want to calculate the uncertainty for weighing result for any weighing result, we have to interpolate the results of the calibration. That is done like this. I'm not going into details of the formulas, don't worry. But again, you have constant contributions and proportional, or contributions proportional to the reading or to the load. So what is done basically is, if you have the calibration results at, in this case, 5 test loads, you will have the error of indication with a respective uncertainty of the error of indication. This is the calibration result. What is done then for assuming or for calculating or determining the uncertainty of any weighing result is to approximate that and interpolate that. You have a respective interpolation, that is this one, and also, of course, interpolation for the uncertainties, that is actually this formula. Next one, as mentioned, is a possible change of the device, and this is mainly due to possible temperature changes. As a calibration lab, we do not know if the temperature might change in the future at the site of installation. So we have to make an assumption of how much the temperature might change at this installation site, and then use this information or this estimation together with a sensitivity coefficient for temperature of a weighing instrument that is usually given in the data sheet of a weighing instrument. And also, sorry, the buoyancy again might change if the temperature changes. And these are again, sorry, quite complicated formulas, and you see the different formulas in the formula. So for example, there are some assumptions for the possible change of the air density. So quite complicated topic, quite complicated formula. It is described and explained in the CG18, but nevertheless, of course, it is complicated to do that correctly. One thing that is mentioned in the CG18 is a possible change of the device. Possible long-term changes of the device. And there we have a problem, as well, for at least for our perspective as a calibration lab. This is usually only known by the user, but not by us. So we just cannot take this into account because we do not have that information. But if it would be available, of course, this would have to be taken into account as well. The next part actually is possible change of use. So as mentioned, during the calibration, you do not use the tear function, but the user might use the tear function of a balance. And if you have, and this is of course again a very extreme example, if you have a strong nonlinearity of the errors over the weighing range. Then if you imagine tearing would have an effect that the determined measurement uncertainty for the net weight is not correct anymore. And therefore, an assumption or approximation of possible effects of the tear function are made. Again, some rather complicated formula which uses the maximum slope of the error of indication and then assumes a worst case scenario for tearing the balance. And another contribution that is mentioned in the CG18, but again, cannot be taken into account without deep knowledge is, of course, possible effects of creep and hysteresis. And this, of course, strongly depends on how the user uses the balance. If you just do a simple weighing by putting something on and reading, you will usually not have creep and hysteresis. But if you do long-term measurements for whatever reason, because you need that for your application, then you might have these effects, and then they should be taken into account. But again, as this is not known, especially to external calibration labs, it just cannot be taken appropriately into account. And one further contribution that is taken into account is again that the user might load the balance more eccentrically than it has been done during the calibration. And this is again approximated by a respective contribution like that. And if we take all that together, we get a so-called global expanded uncertainty. Again, rather nasty formula. But the nice thing, and that is why I made all these blue and red notations, the nice thing is that all these contributions can be assumed to be either constant over the weighing range or proportional. And that in the end gives us the possibility to approximate this formula by a straight line equation, where you have a constant part, that is the so-called axial intercept, usually denoted as A or alpha, and you have a slope of the straight line, which is usually called B or beta. And this is exactly how we state that in the calibration certificate, giving this alpha or beta, alpha and beta, of course. It just looks like this. Now, how can a user really use this equation? Well, actually, it's quite simple. If the user reads a reading, whatever, 123.4567 grams, can simply put that value into the equation. So the uncertainty then of this reading would be this value, the alpha, plus the beta multiplied with the reading. And you can use, for example, Excel or a calculator, whatever, to calculate then the uncertainty for this reading is 0.0011 gram. And that just means, again, with a probability of 95%, the true value is within the range reading minus uncertainty to reading plus uncertainty. So that is how this can be used to calculate the uncertainty of any weighing result by just using the, let's say, comfortable situation that a calibration lab might make the uncertainty determination for you. And actually even more comfortable, our premium balances do have internal functions. So for example, if you have this on your calibration certificate, this is what it would look like. You can simply enter these values into a respective Q app called measuring uncertainty. You have to enter that, all these three parts. And then you can configure this app to just show you, and also in printing it will be given, to give you the measurement uncertainty for any weighing result. And this is really something that I should highlight maybe, that as mentioned in the beginning, the user of any measuring instrument is responsible to state the uncertainty of his measuring results. And now this is quite complicated, as you have seen on the previous slides, but you have the possibility to make it easy for you. Just get a calibration certificate from a respective calibration lab, enter these values into your balance, and then you will get the uncertainty directly with any weighing result. So it can't be easier for you. Now, let me finish actually with a last part with that is the so-called minimum net weight according to Euramet CG18, because that is based on the previously shown measurement uncertainty determination. Now, this is just a slide we've seen before. Again, this is how the straight line equation for the expanded uncertainty over the weighing range is determined. So that means if you have a look at the absolute uncertainty in grams or milligrams over the weighing range of a weighing instrument, it's just a straight line. But if you take a look at the relative measurement uncertainty, so you divide each value by the respective load to get a relative uncertainty in percent, then it will automatically be a so-called hyperbola. And that means, you see it directly here, the relative uncertainty increases to infinity for small loads. And that means if you, for your processes, have a limit that you say, well, I do not want that the relative uncertainty of my measurement result is bigger than 1%, 0.1%, whatever your requirement is, then it's quite easy to say, well, if you don't want the relative uncertainty to be bigger than, let's say, this value, you have to weigh in at least this much. And this is the concept of minimum net weight. If you want to have the relative uncertainty smaller than this value, you have to weigh in that much. Every bigger load will have a smaller relative uncertainty, and every smaller load will have a bigger relative uncertainty. And this is also shown on our calibration certificates. You see, this is actually more or less the same diagram as I've shown here before, the relative uncertainty over the weighing range. So the relative uncertainty over the weighing range. The difference is just this is a double logarithmic plot, because otherwise you would hardly see anything on that diagram. But what you can do now is, and this is usually also given as an example on our calibration certificates, if you, for example, say, I do not want the relative uncertainty to be bigger than 1%, you just follow this line to the relative uncertainty, which is this, what is it, green-blue line. Or if you say, I want to multiply the uncertainty with an additional safety factor, which is quite common, of 2, 3, 5, or 10, then you have to go to the respective colored line. So in this example, we say that the process accuracy or maximum allowed relative uncertainty is 1%. And the safety factor that the user wants is 3%, is 3. Then you have to go to this bright blue line. You just go here, and now you have to read that you have to weigh in approximately 0.1 gram. And it's also calculated here below in this example. So for any process accuracy required for the processes of the user, so that this can be really 0.1%, 1%, 10%, whatever, and an optional safety factor of 1, 2, 3, 4, 5, 10, whatever, the respective weight can be calculated that has to be weighed in to ensure these required process parameters. So I'm coming to the summary. Measurement uncertainty is a general measure of the reliability of a measuring result. and is necessary for reliable conformity statements, pass-fail, and also for determining the comparability of different results. And I did not mention that in the beginning, it is also required by some standards that any measurement result shall be accompanied by a respective measurement uncertainty. It is the user's responsibility of any measuring instrument to determine the measurement uncertainty. So that is the bad news. For weighing instruments, the somewhat good news is that the Euramet calibration guide number 18 provides detailed guidance how to determine measurement uncertainty of a weighing result. But as you might have seen, all these formulas I've shown before are just taken from the CG18. I did not invent them my own. So everything is written in this document, but you may also have thought during the formulas, well, that looks quite complicated. So the implementation of this provided detailed guidance is not that easy. And that's why I personally would also always recommend to let some experts do that for you. And usually accredited calibration labs will provide this uncertainty of a weighing result on calibration certificates. And then, of course, it is much easier than for the user than doing all these calculations his own. And as you've seen, once you have that straight line formula for the uncertainty of a weighing result from a calibration certificate, it is quite easy to either calculate the uncertainty with Excel or even let the weighing instrument do the calculation for you. Yeah, as mentioned, some weighing instruments allow the direct indication of the measurement uncertainty for any weighing result if the respective straight line equation has been determined before. And just to finish that, from the uncertainty of a weighing result, a minimum net weight can be calculated for any process accuracy and any safety factor. Both have to be defined by the user. And let me mention that additionally, because you know there is a minimum net weight also according, for example, according to the United States Pharmacopoeia. Do not mix that up. The rationale between these two considerations is the same, but for small loads, you get a big relative uncertainty. But as seen, if you determine or if you use the minimum net weight according to Euramet CG18, the first difference is there's a sophisticated uncertainty calculation behind all that, and the user can define process accuracy and safety factor matching his processes and applications. So that is a big difference to the USP minimum net weight. It has the same name, but it's not the same value. So I will be happy to answer any questions if you have any. Thank you very much for your attention.
Thank you very much, sir. You have explained this topic of measurement uncertainty calculation in a very detailed manner. We are thankful to you. I hope that certainly, sir, we need some more help from you if you kindly allow us. Sir, some of the participants need this presentation, which you have already shared me. If you kindly allow, can I share this this presentation with the certificate of participation with the participants?
Yeah, so actually, as mentioned, I think the most knowledge is actually taken from the CG18, so it's not internal knowledge, but also internal knowledge. I just have to add that many of these formulas are not self-explaining. So I'm happy if you share it, but just for anyone receiving this presentation, please be aware that you have to read the accompanying documents, so the GUM and or the CG18 to really understand that. But if that is taken into account, I'm happy to share that. And if you share actually the presentation, then the participants will also have my email address. I hope I will not regret that, but if you have questions, I hope it will not too many questions, please feel free to contact me.
Thank you. Thank you very much, sir. Secondly, sir, another request I would like to make. Can you share me a calibration certificate in English, which you people used to issue as per 17025? Because I am aware that you are also authorized by PTB Germany for the verification in Germany. So if you kindly share me a calibration certificate and a verification certificate for the balances and the weights, it would be certainly a great help for us, even for volume also.
So I will be happy to share a calibration certificate for a weighing instrument and also a calibration certificate of a weight. That's no problem. We are an accredited calibration lab. I cannot share verification reports because it is simply not allowed in Germany to perform verification for private companies. It is a authority thing. So we do not do verifications in Germany, but calibration certificates I will be happy to share afterwards.
Please, please. So I will share it with the participants so that they can also understand that what are the parameters they have to mention in the certificates as per the standard of 17025. Thirdly, sir, I would like to request, if it is possible, can you share us your Excel sheets in which you calculate the uncertainties? Excel sheets, but maybe that we are not, or otherwise I will share my Excel sheets to you and you kindly go through it. If anything else or extra has to be added in that extra sheet, in this Excel sheet, you kindly let us know so that this sheet should be uniform all over the world.
Yeah, so we do not use Excel sheets actually to calculate the uncertainties. We have a dedicated in-house calibration software that will do all the the calculations in the background. So we have a software. We, of course, also have respective Excel sheets for a quick calculation of uncertainties, but that is not validated. So what I can recommend you actually is, and just give me a second to share that. What is really helpful and what we use also to validate our software, because you need some independent verification of your calculations. But what you do have in the, let me check if that is the correct screen. There it is, the famous Euramet CG18. And as mentioned, it is free to download.
So generally, for this, we use in India, we use the GUM document, or as per the OML standards, we use the OML documents. So do you feel there is a change in this OML or the GUM document with this Euromet document?
The uncertainty calculation actually is, of course, based on the GUM. I think that is somewhere stated, hopefully here. But for OML, for example, I do know that it is quite common all over the world to calibrate according to OML R76.
Yes.
I do not recommend to do that because the R76 does not give any uncertainty calculation guidance. So from my perspective, the R76 is really a testing procedure for legal metrology. And the CG18 is a calibration procedure. And we really distinguish that. So if we do any legal metrology measurements, we do that according to R76. We test against the respective MPEs. But if we calibrate, we really calibrate according to CG18. You see, it is the R76 is mentioned here as a reference for terminology, for example, but it is really different. And what is sometimes a bit unfortunate, the measurement procedures itself are not directly comparable. So for example, very simple example, the repeatability. According to CG18, you have to zero between each repetition, between each loading. That makes a difference. And of course, you calculate the standard deviation, while R76 determines the difference between the minimum and the maximum of the repetitions. So these documents are really hard to compare. And I personally really recommend to calibrate according to CG18 and to test in legal metrology according to R76. But what I want to show you actually concerning the question for validation of Excel sheets is.
So those are after this R76 2006, it also asks for the calculation of measurement uncertainty during the testing of these navis.
Mhm. Sorry, can you repeat? I did not get the question.
Actually, sir, what happened now in the beginning 1992 standard recommendation of OML, that was not talking about the uncertainty calculation. But now this 2006 this six standard which we are using all over the world of OML, it is basically talking about that during the testing also about this measurement uncertainty calculation.
Mhm.
So whether we have to, what we should do now, because in India we are complying this OML as well as the GUM document. If you, as you are suggesting this Euromet document or this CZ, I think there will be a change in our testing procedure or in our calibration procedure.
Yeah. Of course, I cannot define what has to be done in India, but really from a let's say strict formal metrological view, the CG18 really focuses on calibration. Also, for example, on how users use the weighing instrument. For example, if you just compare the determination of the error of indication, it says in the respective description, it is done how users use weighing instrument. And what do? Actually, they zero the balance, put something on the balance and read the indication. That is how you do it. While in R76, you successively increase the load, which is usually not a typical weighing procedure of a user. So this guide really focuses on giving the calibration result sampling like normal user behavior. And just really to show you for validation of, for example, Excel sheets that you provide for measurement uncertainty calculation. You do have, I think, 3 examples and some of them with options. So it ends up like 6 given examples for which the complete calculation is given here. So you have that example of a typical laboratory balance. All the values that you need are given here, the results of the measurements. And then in the end, you see here's the complete uncertainty budget. So it can be easily compared. So if you have an Excel sheet, just enter these values. And if you have the same results in the end, then your Excel sheet is correct. And you can do that for the 3 to 6, depending on how one counts examples given there. So it's not only for this simple laboratory balance, there's also an example for, where is it? For a higher capacity balance, I think. Let me just further down. Yeah, you see here some higher capacity instrument, 10 kilogram, maximum 60 kilogram, and I think even a more higher capacity weighing instrument. So you have different examples given that should cover the range of applications in the field.
Okay. I hope that this software will be your proprietary item. So I think software we cannot utilize. But as far as your Excel sheets which you are not using now, if you kindly share those, I think that will also help us a lot.
I think I'm not allowed to do that because that really features internal knowledge and also internal, let's say, conventions.
Okay.
Sorry for that, but really, as
No problem.
mentioned,
Ashutosh, we will review. I think that the documentation, Euromet, whatever has been shown here, that is a very useful documentation. And whatever other Excel sheets you are preparing and what other important parameters are to be recorded there, and what sort of maybe a verification sheet needs to be prepared or some corrections need to be incorporated. We'll take a call internally as a policy decision here. So not an issue. I understand the limitations of the organization and Dr. Julian. He is right. He shared great knowledge with us here, and he's explained us if we have questions related to this process and his presentation, any other questions which you are receiving in the chat box, we should be
Yes.
sending and asking him those. My question would be that how does the uncertainties largely probably differ when automatic equipment and a non-automatic equipment, and what sort of a policy is followed in Germany there, and what standards are required in that kind of perspective to Dr. Julian?
So thank you. Actually, the CG18 is really just for non-automatic weighing instruments. There has been published another calibration guide, and I just forgot the number, but we can have a look together actually, for automatic weighing instruments. It has just been published, I think, some month ago. So let me just check if I find it. So I have the draft of that document here. Let's see. So you see this from 2017. It has taken some time, but there is also now published a calibration guideline for automatic catch weighing instruments, for example. And there, of course, it is different because you have to take into account if you calibrate at different speeds of the automatic process and all that. So that is actually, it's more complicated, sorry. And also the uncertainty calculation is much more complicated than in the CG18. So it's a really complicated procedure, but there is also a respective guideline now published from Euramet that should be helpful, I hope.
So there is a document available in the public domain on both the items, and we should probably take hold of that information, which has been published by the European Union and the other countries in Europe. And this is a very good reference material. And we should be looking forward to improving our certificates and the formats of the certificates. He's explained in great detail every stage and what kind of maybe a number is to be taken for each item there and displayed in your verification and the certification process. So it is going to be of great help for essentially for non-automatic equipment here and weighing and calibration systems. So Ashutosh, we can look at some other questions in case there are any.
Yes. Sir, so the questions are some of the questions we have received in the question box and some in the chat box. Sir, one person, some of the participants are asking how to calculate minimum capacity of the balances. Actually, I think if they will go through this Navi, this Navi R76, they can very well easily understand that with the help of this e-value, they can calculate.
From that very formula, so
Yes, sir.
that is applicable for all the items, whether it is automatic or non-automatics. And for weights, it is given in R111. So that way, it can be calculated. If other than the weight is there, if the more than 2 instruments, 3 instruments are there, then the measurement of eccentricity of the all the instrument will be taken together, and after that, a standard deviation of all the equipments may be taken, so that the combined uncertainty may be taken. This is the things I think that is available in the documents, and that documents may be referred. Thank you.
Dr. Julian, will you share this? Are you sharing this sheet?
Yeah, I'm happy to share that. Actually, we provided several white papers to explain, and I just opened this because, again, this is something that is really mixed up very often. You have a minimum weight according to R76. You have a minimum weight according to USP Chapter 41, and you have, as I just presented, a minimum weight according to Euramet CG18. Maybe just to add that for explanation, in Europe we have a clear separation between legal metrology and let's say non-regulated devices. So only for particular applications, you need to have verified instruments. And then you have, of course, to follow R76 also concerning the minimum weight. That is actually whenever it is about money, when it is something that is relevant for court decisions, or if it is about health. For any other application, you do not need verified instruments, and then this standard or this recommendation simply does not apply. And then, of course, you can decide if you are in the pharmaceutical industry, you can follow that USP chapter 41, or actually you have to follow that. And if you are not in the pharmaceutical industry, or if you want to have, let's say, considerations matching your individual process requirements, then you can follow that Euramet CG18. And so we published this white paper about explaining the differences of the different different minimum net weights. So you know that one from R76, and chapter 41 of the USP, Euramet CG18. So you see these diagrams should be familiar now to you, as you just seen them some minutes ago, and also some overview of how these values would be either defined. So for R76, it's a fixed value. For USP 41, you have smallest possible, typical, and recommended values, and also for Euramet CG18, depending on, for example, your process accuracy, it will be calculated here. So I will be happy to share that as well. Let me just actually write down. I'm not getting younger, so I will forget.
Can you share this document? Please, please share this document. It will be certainly of great use. So the next question is, what is the verification scale interval and how to calculate it? Actually, verification scale interval we can simply consider it is the least count of a balance.
Ashutosh, when
Sir.
the matter of uncertainty is there, it is depending upon the users. What type of use of weights and measure, as he described, so that is required. If it is for the scientific measurement, more accurate measurement of uncertainty.
Yes, sir. So the next question is, for repeatability of uncertainty with bell curve, is standard deviation the method to calculate theoretically?
Certainly,
Method?
certainly all the factors will be taken there.
Or other mathematical methods available, please?
Yes.
Dr. Julian, the question is, for repeatability of uncertainty with bell curve, is standard deviation, negative is the standard deviation, the method to calculate theoretically?
I'm not sure if I completely get that question, but oh, sorry. Do it differently. So as I think I've mentioned somewhere in the beginning, maybe maybe here. So you've seen what I've demonstrated and what I've explained is very detailed and, let's say, very correct and complete uncertainty determination. But of course, not every user can do it in such a complicated and complex way. And we're of course aware of that. So what is done in many cases is that it is simply assumed the standard deviation is the dominant contribution. At least for small loads, that is a realistic consideration or approximation, and it is assumed the expansion factor is 2. So that is a really rough estimation of the uncertainty. And as mentioned, you will see that is, sorry, irritating, as you see here. For some application, you see that the standard deviation is the dominant contribution. And then, of course, for this example, this is a real good approximation to just say, well, 2 times the standard deviation. But for other examples, you see, for example, here, where the weight is dominant, you would completely underestimate the true uncertainty by just using 2 times the standard deviation. So it is for a rough estimation, what is my measurement uncertainty? That is fine. But you see, depending on the particular case, you might have different contributions that are much more important and that you do not take into account then. Yeah.
Okay. So the next question is prediction of hysteresis in dynamic weighing with high probability?
In dynamic weighing, hysteresis. So, to be honest, so let me first say that that is a weakness for us, that I mentioned that, because if you do know creep or hysteresis does have a strong effect on my particular application, then you should take it into account. But of course, we as an external calibration lab cannot take that into account because we do not know the detailed procedure. Let me start with that one. Now, the detailed question, in dynamic weighing, if hysteresis plays a significant role. So what you do have is, of course, let's say, sorry to say that, but the more quality the manufacturer has, the less you will have an hysteresis effect of your weighing instruments. That's quite clear. But nevertheless, even for a high quality weighing instrument, if you weigh for a very long time, you do have an effect. So what you have, of course, in the weighing instrument is a mechanics, and this mechanics will have a hysteresis effect if you apply that something longer. So what I recommend is to, of course, at least to get some impression of how big is hysteresis for my application, is of course to make respective measurements or estimations. So for example, what you can easily do is if you do a long-term measurement, afterwards just check the zero return. If you have a hysteresis effect, the balance will not come back to zero exactly after 1 hour of measuring or whatever. If you have a non-significant effect, it should roughly come back again to zero. So you can have an estimation how big is this effect for my particular application. That is what I would just generally recommend.
Okay. Thank you, sir. So the next question is, somebody is asking the class of balance, how to calculate class of balance. Actually, if somebody will go through this OML R76, it will be very clear: class 1, class 2, class 3, class 4 accuracy, depending upon the E value and the number of counts with the maximum capacity. So I think it can be calculated from there.
Just maybe to add, you're right. There are some cases, let me say that from a manufacturer perspective, of course, our marketing defines we do want to have a weighing instrument with a maximum of whatever and a scale interval of whatever. And then usually it automatically follows from the R76 table which class this instrument has to have. There are some instruments that could fit into class 1 and 2 or class 2 and 3 maybe. So sometimes there is a decision to be made by the manufacturer, and then we decide that, well, let's do this as a class 2 instrument or as a class 1 instrument. So there's a few cases where we can define because the table allows 2 classes. Yeah.
Thank you, sir. A very interesting question. Generally, all calculations are depend on E value and minimum E value is 1 milligram. So how we used 1 microgram balance?
Mhm. Yeah, so here we are again at the distinguishing between legal metrology and I don't want to call it illegal metrology, applied metrology. So as mentioned, I think this is really a difference between Europe and India, that in Europe, let's say 80% of the weighing instruments that we sell are not for legal metrology. So the majority is not for legal metrology. And this is really applied metrology. So it does not care about E or the class. Yeah, so you will find in the CG18 some information if the balance does have an E value, or if there is a class, you can do whatever. But usually this is really applied metrology, so this works on any weighing instrument, even if it is a non-verified. And this is also sometimes, or something I should mention, and which is sometimes not known all over the world. As mentioned, in Europe, 80% are not for legal metrology. And if we sell instruments not for legal metrology, they do not have an E value and they do not have a class, because that is defined according to legal metrology. And if you're not working in legal metrology, you cannot define that. So 80% of the devices, approximately 80%, we sell in Europe do not even have an E value. Yeah. So applied metrology does work for every weighing instrument. It does not care about E. And then just to add that, what is also mentioned in the question, a big drawback of legal metrology for weighing instruments is the fact that the smallest possible E value is 1 milligram. And we nowadays have ultra micro balances. So E is, let me calculate, 10,000 weighing steps. And this is, of course, really a problem of legal metrology, that, yeah, no E and no MPE smaller than a milligram or half a milligram is possible, which means that for an ultra micro balance, the legal metrology requirements, the MPE, is really, let's say, ridiculous, because it's 5,000 digits. So a balance, from our perspective as a manufacturer, ultra micro balance can be broken, but it still fulfills the requirement of R76, because the requirements are really weak for a ultra micro balance. This is something that probably has grown historically. The E value may not be smaller than 1 milligram because R111 does not define weights smaller than 1 milligram, and actually it's not feasible to handle smaller weights. So I'm not in favor of defining smaller nominal weights in R111. That would not be my favorite result. But since the R76 was written, weighing instruments have improved. And since then, we have ultra micro balances and micro balances. And my personal opinion is that for this kind of instruments, legal metrology is just not appropriate. But that's just my personal opinion.
Thank you, sir. Thank you. So next question is, could we use stacking of weights while measurement? Stacking of weights.
Stacking of weights.
Yeah.
Okay. So we absolutely forbid that to our technicians. So because if you stack weights, they will have respective scratches after a certain while. And what we do see is, I mean, you can probably imagine that we have thousands of weights in service. And when they come back to our mass calibration lab, we sometimes see that circular scratches on the top. And then it's quite clear this technician has stacked the weights. And this will, of course, change the value of the respective weight. So we do clearly, we cannot forbid that to users, but we forbid it to our service technician to stack weights, maybe for M1 weights. That sometimes maybe it has to be, but F1 and E2 weights, we forbid that to technicians, and we strictly recommend to anyone to not stack the weights.
Okay. What is the acceptance limit in weighing balance as per class wise? Actually, it depends upon the maximum permissible errors of a balance as per R76, or we can calculate the measurement uncertainty of the balance, which is allowed. What do you suggest, sir?
Can you repeat that once more? Because
what is the acceptance limit in weighing balance as per class?
Okay, so yeah, if the question says as per class, then it's the MPE. So then again, we are in legal metrology, and then it's clear it's the MPE according to R76. Again, let me check. We do have a respective white paper that maybe explains that to here it is, to users. So weighing in legal metrology. And then you have that MPEs and respective acceptance limits. So that is really given by R70 or OIML R76. If you are not talking about legal metrology, then any acceptance limit has to be defined by the user. And that is sometimes, or we have a lot of discussions about tolerances or acceptance limits. Many users want to have or want to test against the manufacturer tolerances. We do not recommend that as well, because you might have different environmental conditions than we do have in our production site. So we really recommend to all users to think about what are my requirements. When is a balance acceptable for me and for my applications? And if you define that, then you can define, for example, acceptance and warning limits for your tests and also for a calibration, for example. So what we can do, of course, also is to assess the results of a calibration against respective user specifications. That's possible. But there's only one, let's say, standard document giving acceptance limits, and that's the OIML R76. And that is, again, only applicable to legal metrology instruments. So if you're outside of legal metrology, you do not have standard acceptance limits. And therefore, we recommend to users, please define your own specifications.
Okay. Thank you, sir. Sir, another question is, can we calibrate heavy capacity weighing balances by using M1 class weights? I think it is not, because, for example, if we are calibrating a weighing machine of, let's say, 1 ton, 10 gram, it requires at least F1 class weights to calibrate. What is your suggestion, sir?
So from a strict formal view, you can calibrate any weighing instrument with any weight. It will just increase the uncertainty. So for example, you can calibrate, of course, also, calibrate an ultra micro balance with M1 weights. It's possible. It would just mean that you respectively increase the uncertainty. Yeah, so if you appropriately take into account the respective uncertainty of the weights class, then you can do it. So that is the formal view. What I would recommend again is to, if you have that respective Excel sheets that you mentioned, you can simply add or enter maybe a E2 weight, F1 weight, M1 weight, and then check, does it make a difference? So you see for already the 70 kilogram weight, balance, we're using F1 weight, but you see the weights are not important. You see, this is the calibration uncertainty. So if I used M1 weights here, this bright blue would be a bit bigger. So you would only slightly increase the calibration uncertainty. Yeah, but if you have, for example, a scale interval of 0.1 gram, then it might be bigger what you do. So it really depends on the particular situation. Generally, just to mention that, our accreditation says that we use E2 weights up to 10 kilogram, F1 weights up to 300 kilogram, and M1 weights then up to, I think, 6 tons. So that is what our accreditation looks like. And just to give you a feeling which weight should be used where. But you can also calibrate, let's say, 150 kilogram balance with M1 weights. That's possible.
Thank you. Thank you very much, sir. How to address the drift induced by environmental conditions, particularly in case of highly sensitive balances like 5 digits and 6 digits balances?
So I'm wondering what exactly is meant here by drift induced by environmental conditions. What is taken into account in the uncertainty calculations I've demonstrated is temperature changes. So that is taken into account as long as you do not have, let's say, too strong temperature fluctuations. If you just have temperature change in your weighing room of, let's say, 5 Kelvin or 10 Kelvin, that is appropriately taken into account in the respective calculations. All other environmental conditions, if they drift slowly, should not have a significant effect on the result.
Okay. So one very good question. If balance is 100 kg with D value 10 gram, if we keep 50 kilogram on balance, then what is the acceptance criteria for it?
Yeah, so maybe that's the same answer as before, actually. If it is a legal metrology balance, then you would have a class, you would have an E value, you can calculate the MPE, and then I don't know, would be probably, 5 gram or 10 gram, sorry.
Yes.
Yes. Then it's clear if you have application or a weighing instrument outside of legal metrology, then it really has to be defined by the user. So if you, maybe just to explain that, we also as manufacturers do not state specifications for the deviation of a weighing instrument. And that is sometimes that users ask us, why do you not state that value? Well, simply because the deviation of a weighing instrument depends on so many factors, the environmental conditions, but also, of course, adjustment. So let's just consider this. You have a perfectly working balance that is absolutely perfect. But now you can de-adjust that balance by putting on a wrong adjustment balance, and then it, of course, will indicate wrongly. But it is not the fault of the instrument, it is the fault of the user in that case. So it is easy to make a balance show a big deviation or zero deviation. It's really easy, but what you should do, of course, is to do it reasonably and to have respective calibrations. And then again, I recommend to consider from a user or from a process or application view, what do I accept?
Good. Thank you. Thank you very much, sir. I think that this is a very wonderful and interactive session in which you have replied all the questions. Thank you very much. First of all, I would like to thank you, sir. You came and you have taken your time on being on Saturday and Sundays. and took this whole lecture and the question answer session. I would like to thank you, sir. I would like to thank our joint secretary, sir, who is here and who has simply enlightened us, who has explained a lot of things and who has basically motivated us. I would like to thank our joint director, Mr. B. N. Dikshit, sir, who is always with us for making any type of good activity. And sir, I would like to thank my NIC team also, who is basically working on Saturdays and Sundays for these type of programs every week, being holidays, with all this. And the last but not the least, the participants. We have large number of participants over here, and we are going to issue the certificates to all participants who have done the registration and participated in this program. With this, I would like to thank all. Sir, I'm waiting from your side. As you will send me the presentation. As soon as you will send me the presentation, immediately, sir, I will share it with all the participants. Thank you very much, sir. Thank you. Thank you.
Thank you very much. It was a pleasure for me. And have a nice weekend, everybody.
Thank you, sir. Thank you. Well, thank you. Same to you.